In one of our first topics this semester, we distinguished between local area networks and wide area networks, where we said wide area networks covering a large geographical area, say across a city, between cities, between countries, so across the globe, whereas local area networks are typically connecting end user devices, the things that you and I use, our laptops, PCs, mobile phones, and so on, connecting them in a small area, for example, within our home, within an office building, within a university campus. Different technologies are used for each type of network because they have different requirements. Wide area networks are normally operated by some organisation on behalf of the end users. So you and I don't have our own wide area network. We may have our own local area network though. That is, at home we have our own cables, we pay for the cables, our own switch or router, and our own end devices. So wide area networks normally owned and operated by an internet service provider or a telecom company, and they rent that network to the users. Whereas with local area networks, it's usually the organisation that owns the end user devices, the PCs, the laptops, that operates the network. They design them and build the network themselves. So that leads to different requirements and different options in how you can select the technologies to support or to build the network. Local area networks need to support data within the network. Okay? If you think about the LAN inside this campus, there may be traffic that goes between the computers inside the campus, as well as traffic that goes from the computers from inside the campus to outside, out to the internet. So usually a LAN needs to support traffic internally, for example, me accessing a local web server, staff accessing a local database. So there's data transfer inside the network, as well as we want to access stuff outside of the LAN. For example, access websites, access the Rangsit campus and other resources. So inside the LAN we need to support typically higher data rates than in wide area networks, because we need internal communications. So that's the summary of the difference between wide area networks and local area networks. And in fact, that was mentioned at the start of the semester. I've just cut 3 or 4 slides from that topic on LANs. So this is maybe, I don't know what slide number is, I can't remember, but a fair way through the topic on LANs that you have in front of you. Just a reminder, and in fact we said this last week, with local area networks, some of the most common technologies have been developed by this organisation IEEE, and they've developed local area network standards for wired LANs, and the standard number is 802.3, for wireless LANs 802.11, and there's some similarities amongst them. Of course, wired versus wireless is different, but some of the protocols they use, in your assignment you studied and you gave me a description of CSMA, or at least you saw the acronym. Similar techniques have been used in LANs, wired LANs. So they have some similarities in the link control and the medium access control across different technologies. So wireless LAN or Wi-Fi, wireless personal area networks, Bluetooth, larger wireless networks, WiMAX, and different wired LANs. Most of the LAN technologies are concentrating on the physical and data link layer. So it's how to communicate inside this one local area network. We're going to see in the next topic, which is our focus, that, okay, what if we want to communicate outside of that network to a network that uses a separate technology, and that's where the internet protocol comes in. But for now, let's assume that across the world there are many LANs, and they may use different technologies. SIT may use one technology inside this campus, and then another university inside their campus may choose a different technology. Okay? And across over the last 30 or 40 years, as the networks have been used, then many different organisations have chosen different technologies to suit their requirements. What else do we want to say about LANs? That's about it, except for addresses. An example configuration, and you may have seen this in wireless LANs as well, or a similar setup. This is an example of a configuration of a local area network with multiple segments. We see some PCs, the end user devices, and a common configuration in LANs is to use a switch, this star topology, where we have this special device called a switch, which all the end user devices have a cable going into that switch, and then that switch has a cable going into other parts of the network, in this case another switch. So that's what we have in this campus. This PC here on the desk has a LAN cable, and that LAN cable goes through the cavities in the wall and the ceiling and goes downstairs to the third floor and has that cable, if that's the PC on the desktop, has a cable going into a switch, and the switches in this building are on the third floor in the computer centre. And the PC in the next lecture room also has its own cable going to that switch. And same with other lecture rooms and other offices. Let's consider the LAN across this campus to be all one local area network. So this may be one building with multiple computers connecting into the switch, and in the other building, of course, there are office computers all connecting into a switch, and maybe lab computers all connecting into another switch, and maybe some servers, web servers, email servers, database servers connecting into another switch, and then again those switches connect together. So in fact they all can communicate with each other by sending via those switches. These are referred to as Ethernet switches or LAN switches. That's our local area network, say across our campus. So if we want to communicate with anyone inside the campus, we would just go via those switches. Of course, sometimes, or most of the times, we want to also communicate to people out on the internet. So that's external. And we will see in the next topic that we call this device that connects our LAN out to the internet a router. We'll describe a router shortly. There are different configurations of LANs. What you're going to study next semester in computer network architectures and protocols is the details of how LANs work. So you'll see the different options for the configuration, the ways that protocols like 802.3, the MAC protocol and the physical layer work. So you'll see that in depth next semester. We will not try to cover it now. And you've seen some of it in the assignment, at least for wireless LANs. One thing that you've also seen, and it's worth mentioning here because you may see it again, or we may refer to it in the next few slides or the next topics, is the format of the frame used in Ethernet. And it's about the same format as what you saw with Wireshark when you captured with the wireless LAN traffic. And in your assignment, you drew a frame or a packet that looked like this. It had some data. Maybe it was a HTTP request. And it was put inside a TCP packet. So there was a TCP header, which is inside an IP datagram. So there's an IP header. And then there was some Ethernet header here. Or at least in a wired LAN, we put this, so this is the network layer, transport layer, application, and this is the data link layer. And with wired LANs, the name of the protocol used is Ethernet, or 802.3 to be precise. What does this header look like, this part? It's shown here. That's what this diagram shows, but it's shown in the vertical form. We can summarise and say that this is a frame. A common approach to call this as a frame. And inside this header for the frame, there are different fields. We'll come back to the first two in a moment. Let's focus first on the frame here. The destination address, who we're sending it to, destination, source address, and we see that each of those are 6 octets. How long is an octet? How long is an octet? Not 3 bits. 8 bits. An octet is 8 bits. Same as a byte in our course. Okay, it's just the formal term to refer to 8 bits in this case. So it's 6 bytes. 6 bytes destination address, 6 bytes source address, a 2-byte length or type. Typically it's the type, which indicates what is inside this frame. So it would be a number to indicate, in this example, the type is an IP datagram, because inside the Ethernet frame is IP. It wouldn't give the letters IP, there'll be a number that represents the Internet protocol. And if we had something else inside, it would get a different number in the type field. The destination address would be the address of the computer that sent this frame, or is sending the frame, and the source is who they're sending it to on the LAN. Then we have, in fact, the data here, and at the end, we have a trailer, which is says a frame check sequence, usually, so for error detection. Again, we've only mentioned one part of error detection. We mentioned the example of parity bits, but it's some extra information such that when a receiver receives this, they can check, are there any bit errors inside this frame? They cannot fix them, but they can at least detect errors, or detect a large percentage of errors. So there's some extra information included, in this case at the end of the frame, for error detection. It's 4 bytes in length. The two at the start, the preamble and the start of the frame delimiter, are normally considered part of the physical layer. At least we will consider them part of the physical layer. And you would not see them in Wireshark. When you captured traffic in Wireshark, you would see probably at least these fields, this information. I don't think you see the error detection. I cannot remember, but I don't think it's shown in Wireshark. Wireshark can only show you what your operating system sees. It cannot show what the hardware may remove. So Wireshark, as the piece of software, cannot show you the exact structure of the physical layer header and so on, because that's processed inside the hardware before it gets to Wireshark. So it only sees, I think, the destination, source address, and the type. That's a typical structure of an Ethernet frame, and it's the same structure used, or a similar structure is used for wireless LAN. Slightly different, but it at least has the source and destination address, and it has a few more fields in wireless LAN. And the maximum size of the data is typically 1,500 bytes. So we have 1,500 bytes here, a maximum, plus 4 bytes of the error detection, and another, what have we got, 14 bytes header here, 14 plus 4, another 18 bytes of header. You'll typically see an Ethernet frame, a maximum size of 1,518 bytes. 18 bytes of header plus trailer plus 1,500 of data. That's the maximum size. It can be smaller. We just give that because it's a common frame format that you'll see in Wireshark, in the lab next semester, and sometimes when we refer to some examples in the Internet protocol. The last thing, and again we've mentioned this in another lecture, these addresses. What do they look like? Well, there's a standard that defines that there are 48 bits long, 6 bytes, 48 bits, and they have some structure. Of those 48 bits, they're not just random. how they're structured is that the first 24 bits, the first half, is a unique number which is assigned to manufacturers of devices. And it's assigned by IEEE. So if you want a company wants to manufacture LAN cards, what they do is they go to IEEE, and IEEE gives them a 24-bit unique identifier. Two different manufacturers would have two different 24-bit sequences. When they manufacture your card, they take their assigned first 24 bits and then select a unique last 24 bits. So the total 48 bits in the world should be unique. So the idea is to have globally unique addresses. My LAN card will have a MAC address or a LAN address which is different than yours. Turns out nowadays you can change them in software. So you can change them, and as a result they're not always globally unique. But the idea is that they're unique in that first 24 bits identify the manufacturer, the last are assigned by that manufacturer to your device. So it should identify the device by that manufacturer. They're 48 bits in length, but for simplicity they're shown in hexadecimal usually. So with hexadecimal they're shown in 6 two-digit numbers, 12 hexadecimal digits. They're common not just in Ethernet wired LANs but in other technologies. There are a newer 64-bit address which is not so common, or we don't see it so much at least in the technologies we use. And there are other types of addresses, but that's a very common type of address. And to finish, let's have a look at an example. On my computer, I have my wireless LAN. So this is the wireless LAN interface. I have another one I'll show at the top. The hardware address is what we were referring to, the LAN address, the hardware address, or the MAC address. It's this 48-bit number, which is a 12-digit or 12 hexadecimal digits. So in this example, my wireless LAN card, these 6 hexadecimal digits are mapped to 24 bits. They should represent the manufacturer. The company that created my wireless LAN card. And the remaining 6 hexadecimal digits, 8E, E4, 95, have been assigned to my wireless LAN card by the manufacturer. Okay? So when they create wireless LAN cards, that company gives a unique last 24 bits to each device they create. And if I just scroll up, you can. It's here, down the bottom. This is my LAN card, my wired LAN card. And it has a separate address, 002454. The first 6 digits assigned by the manufacturer, and then 06CBEC. And if you check on your mobile phone, you'll find, if you can find the details, you'll see the MAC address or the hardware address, and it should be another unique value. IEEE is the organisation that assigns those first 6 hexadecimal digits to companies, to manufacturers. And they have a website that lists which companies have which 6 digits. So let's have a look at that website and just do a quick example. So on this website, what you can do is search. That is, you type in the first 6 digits and it should return you who manufactured that device. Let's try mine. And the format is 00265E, which is my wireless LAN card and search, and it returns who manufactured my wireless LAN card, Hon Hai Precision in China. Okay? They're a company that makes many network devices and other computer devices. And if we try the other card, the wired LAN, who manufactured? Okay, so we can see in this case different manufacturers of the wireless LAN chip in my laptop and the wired LAN interface in my laptop. And you can check in any of your devices who's the original manufacturer of that device. And that's simply from this first 6 hexadecimal digits. You'll see these 48-bit or 12 hexadecimal digit addresses in many examples and in many practical situations. And that's it on LANs. That's all we want to say, because it's just enough for us to understand how the internet works. Any questions? It's just a summary so we can move on to the next topic. Yep.
So how about this? How about this one?
The last 6 hexadecimal digits are assigned by the company. So for my wireless LAN card, IEEE gave Hon Hai Precision these 6 digits, and when that company manufactures wireless LAN chips, sending them out of when they create them in the factory, they assign a unique 6 digits to each device. So if you can imagine all the chips coming out of the factory, the first one gets one value, the next one gets a different value. And it's up to the company to make sure they're unique. Okay? So it's just a different number. With 24 bits, we have what, 2 to the power of 24, or what is it, 16 million. 16 million different addresses that they can assign. If they run out, then they can get a different identifier here from IEEE. Any other questions before we move on? You can check on your tablet what your MAC address is, and you can find who manufactured your wireless LAN card, your Bluetooth interface in some cases. So now let's look at the main topic, and one of the most important topics is how the internet works. In the last 2 topics, remember, we had switching and routing. We looked at the general concepts of, in a network, how do we get data across a network, and how do we find a path through the network? Well, the internet, as we use today, is one such network. Okay? So what we're going to cover in this topic is how, in the internet, we get data across the network, and we'll see that we use datagram packet switching. So with switching, we had 3 approaches: circuit switching, datagram packet switching, virtual circuit packet switching. In the internet, we'll see that it uses datagram packet switching. Okay? And we'll go through the internet protocol. We'll talk about routing in the internet. And we'll define some terminology and look specifically this is generally about internet protocols, but how does the internet protocol work? So now we're moving on to a specific protocol, not general concepts like switching and routing. There are other protocols. It's just that the internet has become the most popular, and the internet protocol is now used in most networks. Let's first talk about the motivation for internetworking. And this is just a repetition of the slide we had before for LANs. That we have local area networks and wide area networks. And different technologies are used in different local area networks and wide area networks. SIT may choose one technology. Another organisation inside their office may choose a different technology. And same for wide area networks. To connect between our two campuses, we can use a wireless link, WiMAX for example. We can use technologies called PDH, SDH. We could use ADSL to connect between campuses, optical fibre, copper wires. Within different wide area networks, again, different organisations will choose different technologies because they have different requirements, and over time things have changed. So what we would like to do is, considering all these different LANs and WANs across the world, connect them all together. Allow any computer to communicate with any other computer, independent of what technology they use for the local area or wide area network. So even if I use wireless LAN in this network and I want to communicate with someone in the US who's using some old technology, token ring, and the networks between us are using many different technologies, we'd still like to allow those computers to communicate. And that's what internet working aims to achieve. To allow us to connect these different networks, LANs and WANs together, internetworking. Different types of networks in particular. Can your Bluetooth interface on your phone communicate with my wireless LAN interface on my laptop? No, different technology. They at the data link layer and the physical layer level, they need to use the same protocol to be able to communicate. So this situation arises, how do we enable them to communicate with each other? Well, we introduce another protocol. In this case, we'll see the internet protocols, so that from your Bluetooth interface, you send to some intermediate device, which then sends it onto my wireless LAN interface on my laptop. And that data communications is performed using the internet protocol. And that allows your mobile phone using Bluetooth to send data to my laptop using Wi-Fi, even though they have different technologies. So that's what we're trying to achieve with internet working. We'll use this example to illustrate or to introduce some terminology. So across some areas, say across the world, there are many different LANs and wide area networks. So this is a very simple example where we have 6 local area networks, and I use clouds to represent those local area networks. So the cloud here, let's say the LAN inside one or network has some PCs connected to a switch. And some switch connected to some other device, which we'll see in a moment. That may be one local area network. Instead of drawing the switch, the internal devices and the PCs, in this diagram we just draw a cloud to say it represents some network. That's what this cloud here represents. There could be hundreds of PCs in here, there could be one PC, there could be many different cables and so on. We don't care about the details. We just say that this is some local area network. And here's another local area network and so on. Same with the wide area networks. The link from this device, which is, say, here, across the wide area network to these next 2 devices could be anything. Or it could be many different technologies. It could be a wireless link from here to here, or it could have been an ADSL link or an optical fibre or any technology that we have available for wide area networks. So there are many different technologies that can connect them. So instead we just draw a cloud that say somehow these 3 devices are connected via a wide area network. That's this WAN 3 here. Okay? So the clouds represent individual technologies inside that LAN or wide area network. So across the world we have many different LANs using different technologies. And because they use different technologies, they cannot communicate with each other. If we're using Bluetooth here, your mobile phone, and someone here is using wireless LAN, Wi-Fi, they cannot communicate directly with each other. So we use internet working to allow them to communicate. Internet working is performed by routers, and that's what these devices are. Okay, the three here that I've drawn are routers. A router connects two or more LANs or wide area networks together. That's the idea. Here we see a router, it connects one LAN, or LAN 4, to the wide area network 3. It connects two networks together. Which one? This router here connects three networks together. LAN 3, LAN 6, wide area network 2. So a router generally connects two or more networks together. That's its role, connecting different networks together. And note, so this router here, on this side, it's using one technology, let's say Ethernet, wired LAN. And on this side, it may be using a different technology, let's say ADSL. So a router will connect networks often using different LAN or wide area network technologies together. That's its role. In the internet, routers are packet switches. So we've covered switching, and we distinguished between circuit and packet switching. Routers are packet switches, and they operate at the network layer. So we're now focusing purely on the network layer in our 5-layer stack. And in fact, in the internet, specifically, they are datagram packet switches. We use datagram packet switching. That is, going back to the switching lecture, we send a packet to this one. This finds a path through the network, sends it to the next switch, and eventually to a destination. So these are just packet switches. And we use our normal packet switching, particular datagram packet switching, to deliver data from one computer on a LAN to, say, another computer on a different LAN via those packet switches. So some terminology. The routers are nodes that connect networks together, and they operate at the network layer. So these are our routers in this example network. We can refer to these individual LANs and wide area networks as subnetworks. The individual component networks we can call subnets or subnetworks. Internetworking is this process of connecting different subnets together. So in this slide, how many subnets? How many subnets do we have? Okay, so we have 9 subnetworks in this example network. This is a network, this is a network. There are 9 different networks. We'll generally refer to them as subnetworks. And altogether we get another network. Okay? Internetworking is the process of connecting these subnets together via routers. An internetwork, or shortened to an internet, is the resulting network. Here we have one internet. So we call this entire network an internet, or an internetwork. So this internet consists of 9 subnets in this example. The internet that we use on a daily basis consists of hundreds of thousands of subnets. Okay. But we could build our own internet in our lab or wherever we like that doesn't connect to the larger internet with, say, 9 subnets and this set of routers, and we'd call this entire network an internet. When we're generally referring to an internet, we usually use an lowercase I for internet. When we're referring to the network that we use on a daily basis that uses the internet protocol, it's usually an uppercase I here, the internet. So the concept is we can build an internet. What we use on a daily basis, confusingly, we call the internet. The internet is an internet that uses one specific protocol called the Internet Protocol. We've said this before. Routing is the process of discovering the path across a network. Forwarding is the process of sending the data along that path. Here's our network. We need to find a path from some computer in LAN 4 to a computer in LAN 5. Routing needs to find the path. Which routers do we go via? Forwarding is sending the data across that path. We distinguish them. We can talk about a packet switch, some device that performs packet switching. In the internet, the packet switch is a router. Okay, so in fact we use a different name for them. A router is just a packet switch, but we now start to call it a router when we talk about internet working in the internet. So these are routers. They're also packet switches in our knowledge of switching. We know there's also circuit switching. Another confusing thing. Inside our LAN, you know that there may be a switch. So this computer connects via one cable down to a device downstairs. That device downstairs is called a switch. But it's different. It's not a router. We'll use the terminology, it's an Ethernet switch or a LAN switch. You can buy them, or a switch or a hub. It's not our packet switch in this network, in the internet. Uses similar technology, but we distinguish that's the device inside the LAN. So it gets confusing because we have different types of switches. Remember that routers are packet switches, in particular datagram packet switches. There are other types of switches as well. So an internet is made up of multiple subnets. Those subnets are connected together via routers. Those routers are datagram packet switches. Any questions on the terminology before we move on? Everything okay? You sure? Okay. So, an internet working protocol has the job of getting data from source to destination via an internet. And there are different internet working protocols that have been developed. One of them that we're going to spend our time on, and which is used mostly today, is called the Internet Protocol. Okay? It's a specific instance of a general internet working protocol. So what should a general internet working protocol do? A protocol that allows us to send data across this internet. There are many things that it may do. Provides links between subnets, subnetworks. Provides routing and delivery of data, so for example datagram packet switching. Of course we'd like to get data across a network, but sometimes we'd like to manage that network and know the status of the network. Know if this router is working correctly, or if there's a problem with a host or a computer here. So some internet working protocols also include features for managing and maintaining the status of the network. Error reporting, see if there's something is wrong. So there are different features that an internet working protocol may provide. Importantly, an internet protocol should work without requiring changes to the subnets. Let's say this is across the globe. There are many wide area networks and LANs, all operated by different companies. Some in Thailand, some in US, some in Europe. So an internet protocol should allow the computers on each network to communicate with any other computer without requiring changes to the technology used in the subnets. So if this LAN 5 uses wireless LAN, an internet protocol shouldn't require the LANs to all use wired LANs. Okay? We should be able to choose whichever technology we like inside the LAN and still be able to communicate. So the problems with that is that the different subnets may have different addressing schemes. In Ethernet, we have this 12 hexadecimal digit, 48-bit addresses. In other networks, we have different types of addresses. They may have different maximum packet sizes. We saw an example. Our maximum packet size or maximum frame size for Ethernet had 1,500 bytes of data. Another technology may have a different maximum size. Okay? We need to cope with that. Different parameters for the protocols. For example, timeouts. If we're using a ARQ scheme to send our LAN frame and we wait for a response, an ACK, how long do we wait? Well, that's a parameter of the protocol, a timeout. One network may use one value of the timeout, another network use different values. In the internet, we somehow need to cope with these differences. Some of these networks may use error recovery, ARQ schemes. This one may use stop and wait. This one may use go back N. This one may not use any. Okay, it's up to the technology to choose. Still, we should be able to get data from source to destination, even if they use different error recovery schemes. They may use different routing, different security techniques. So they're between the different subnets, each subnet may be using different technologies. An internetworking protocol must work irrespective of all those differences. It must cope with those differences. We're going to look at one internetworking protocol. It's called the Internet Protocol. It's what we use every day. Okay? It's what's used in the internet. There are others, but in the past they've been developed and they either were old and did not become popular, like the Internet Protocol, or they're used for very special purposes. The main one used today is the Internet Protocol, IP. IP does some of these things. It meets some of these requirements. Those that it doesn't meet are left to other protocols, which also fall within the TCP/IP 5-layer stack. So let's first focus on the Internet Protocol. The next topic focuses on TCP. How does IP work? IP is an internet working protocol. It's used in the internet. There have been different versions, so it's improved over time. The version that's used most today is IP version 4. The next improved version is IP version 6. It's available, it works, it's in use in some networks, but it's not as widespread as IP version 4. So in this course, we're focusing on IP version 4. In other courses, you may cover IP version 6. IP is an internet working protocol. There are other internet working protocols, but just not as popular as the Internet Protocol. There's something called IPX, X25, and others. Okay? So there are others. It was initially developed in the US Department of Defense, but now it's a standard created by or produced by the Internet Engineering Task Force, IETF. What does it do? What are its features? It's a connectionless protocol. In simple terms, we do not create a connection before we send data. In some protocols, you establish a connection and then send data. IP does not do that, so we call it connectionless. We'll see some details of that. It operates at the network layer, and it uses datagram packet switching. So of those three types of switching that we saw, IP uses datagram packet switching. The simplest of the three. There's no connection setup. Just send out packets. Okay? It provides data delivery. That is, when we send our packets, it tries to get them to the destination. That's the goal of our Internet Working Protocol. It defines an addressing scheme. And we have a few different slides, or quite a bit to cover on the structure of IP addresses. You've seen IP addresses. How are they structured and what do they mean? That's part of the Internet Protocol. And we'll see there's some ways to break an IP or break data into multiple fragments. Fragmentation and reassembly. It doesn't do much compared to alternatives. It simply allows us to send packets across the network, gives us some addresses, and when necessary allows us to break data into smaller fragments and send individual fragments. What it doesn't do, it doesn't allow us to set up a connection control. It doesn't do any error control. Our ARQ schemes, stop and wait, go back in, IP does not use them. Okay? It doesn't send a data frame and then wait for an ACK. It just sends data. Okay? There's no flow control. There's no sliding window. You'll be happy because it's very simple. IP, we just send our data. In fact, those mechanisms, which are generally needed by some applications, are left to TCP. So the functionality is shifted elsewhere. It doesn't do status reporting. Status reporting is, for example, is this device working? So you want to know if another device in the internet is working. So report the status of that device. IP does not provide that feature. There's another protocol that does it, called ICMP. Ping, for example, uses ICMP. It doesn't provide priority or quality of service. That is, I send my packet, you send your packet, IP treats them the same. One doesn't get higher priority than others. Okay? It treats everything the same. Sometimes we'd like to, for example, give higher priority to my video traffics and lower priority to your web browsing traffic. IP does not provide such a feature. IP on its own doesn't provide any security, any encryption. Again, there's an extension called IPsec that does do it. IP on its own is very simple in that it doesn't provide a lot of these features which are shifted to other protocols in the internet. Okay? And that's one of its advantages. It's simple, it can be deployed easily on different computers, and it's generally efficient to operate in a large network. This is how it fits in our 5-layer stack. From physical layer up to application layer, we're focusing on the network layer. Physical and data link layer, there are many different LAN and wide area network technologies. Some examples listed here. IP sits here. It's the center part of our internet stack. We'll see that there are some supporting protocols like ICMP. There are other routing protocols considered in the network layer, but IP is the main part. Above that, there's things like TCP and UDP, and then our application protocols. So the internet stack is centered around the internet protocol. What we'll do is go quickly through the structure of an IP datagram and then skip a few slides and look at addresses and then come back and see how IP works. So what we do, if we come back to our network quickly, we have a computer on one local area network, wants to send data to a computer on another local area network. We use datagram packet switching. Somehow we discover a path through the switches via the routers. That somehow is performed by a routing protocol. Our previous topic looks at different aspects of routing. Once we have a path, the source creates what we call an IP datagram. Sends that IP datagram to the first router, sends it to the next router, and eventually to the destination. So the question now is, what's the structure of this IP datagram? In particular, the IP header. This is an IP datagram here. And the structure is shown in this diagram. Let's explain what the diagram shows. We read it row by row, okay, left to right. So this is the start of the IP datagram, and then we look, there are different fields in the header. So this is the header here. There are different fields, we'll describe them in a moment. And then we read the next row, and so on. And then we have our data at the end. And that may be variable size. This diagram shows each row is 32 bits in length, 4 bytes. That's a slightly different way to how we've drawn it in other lectures. For example, I've drawn the IP header like this, just as a rectangle here, and sometimes I listed the fields here. This is just a different way to view it. These are the fields, the first field, the second field, and then we go on until we get to the data, and then have the data here. The header has 20 bytes of required fields. 20 bytes, we see each row is 4 bytes, 32 bits, and 1, 2, 3, 4, 5 rows here. So 20 bytes here. We can sometimes have optional header fields, which makes it bigger. And the data can be different sizes. It must be an integer multiple of 8 bits, so 1 byte. And the maximum size of the header plus data is 65,656 bytes. Why? Because we have some field here which tells us how long it is. And that field is 16 bits long. 16 bits means 2 to the power of 16 or 65,656 different values. So if we have 1 byte of data, then the total length would represent the header plus that 1 byte. If we have 1,000 bytes of data, then the total length would be the header plus that 1,000 bytes. So we have a limit on the total amount of data in our datagram. All right, going through at least some of the fields, and the next slide gives a short description of them. The version, we're using IP version 4. If you're using IP version 6, this would be a different value. Okay? H length, the header length. Normally the header is 20 bytes, but we may have options. So if there are options, we specify how long it is. So the receiver knows where does the header start and where does the header finish and where does the data start. Because the receiver looks in here and realizes, okay, there are some extra optional header fields, so I can distinguish between what's header and what's data. ECN, we're not going to focus. It's a way, it's an optional way to give, some networks can give priority. But IP doesn't specify how to use that. Other protocols do. Total length is what we've said, the total size here. Identification can be used as some sequence number in the datagram, so some number, some ID of that datagram. Flags are normally 1-bit values that indicate the meaning of this datagram. So we see the flags, 2 bits there are used for fragmentation and reassembly. Later we'll describe how fragmentation and reassembly works. So we'll see those flags come off later. Same with the fragment offset. We'll describe that later. Time to live. That's like our hop counter. Remember with flooding, we saw an example of a hop counter. We start with a value 3, we send it to the first device, that reduces to 2, to the next device, to 1, once it's at 0, we do not send any further. That's like a time to live value. The source sets a value, let's say 3. They send it to the first router, that router decreases it to 2, to 1, to the next router. Once it's at 0, that router will not send it anymore. It deletes the datagram. It's dead. It doesn't live anymore. So it's a way to limit the lifetime of the datagram in the network. Used mainly for, or you can use it for error reporting, but designed so that one reason is that a datagram will not be sent forever in the network. Let's say there's some error somewhere in the network and the datagram goes from one router and then back to another route, the source router, and keeps going back between routers. It'll do that forever if there's some error in the network. With the time to live, eventually that TTL will get down to 0 and one of them will stop sending. Okay? So there are different uses for the TTL. The protocol field indicates what is inside this IP datagram. In this case, there'll be a number, what have we got? An 8-bit number that indicates what is inside the IP datagram. For example, if it's a TCP packet inside, there'll be a number to indicate TCP. Do we have an example? From memory, the number for TCP is 6, I think. So in this example, the protocol field would have the number 6, which indicates to the receiver the data is in fact TCP data. Header checksum is for error detection across the header, to check that there are no errors in the header. Not the data though. That is, it doesn't check if there are any errors in the data, only in the header. There are some optional fields, we'll not cover them, and then the data. And we have a source and destination address. Source address is the computer that created this datagram. Destination address is the eventual or final destination. If my computer is sending to the Facebook web server and I send via multiple routers, my computer creates an IP datagram. The source address is that of my computer. The destination is that of the Facebook web server. Okay? So the source is the original source. The destination is the final destination. We'll see, even as it goes via routers, those values should not, in most cases, change. Rather than going through, or right now, the rest of how IP works, let's jump ahead and see what is the structure of these IP addresses and use some examples to illustrate them. And then we'll come back and see how IP works, okay, tomorrow. For the last 15 minutes, let's look at some example IP addresses. Let's, as an example, look at the IP address on my computer. What is the IP address of my computer, my wireless LAN interface? Can anyone identify it from that information? It tells me some information about my IP address. What is it? 10.10.99.251. Okay, so here in this program it calls it the INET address, the internet address. So in my example, 10.10.99.251 is the IP address for my computer. There's also this internet INET 6 address. That's for IP version 6. You see it's much longer. With IP version 6 we have different structure of addresses. We're going to focus just on IP version 4, an internet address. 10.10.91.251. We read it as 10.10.99.251. How many bits in an IP address? How many bits? How many bits in an IP address? Not 12? Go back to the structure of the IP datagram. In the IP header, we include an IP address, both the source and destination. Look at the length. 32 bits from 0 up to 31, 4 bytes. An IP address, an IP version 4 address, is always 32 bits in length, always. So we have a 32-bit value. What is this? This is not 32 bits, this is 4 decimal numbers. This is just a convenient way to represent those 32 bits. Okay? This is an IP address, 10.10.99.251, but in fact it's just a human-friendly way to represent a 32-bit value. Writing down a 32-bit value and remembering one is not easy. But I could remember my IP address is 10.10.99.251. If I looked at it several times, I'd remember that. But remembering a 32-bit value is not easy. So we convert the real 32-bit address into these user-friendly, well, somewhat user-friendly addresses. Okay? All we're going to do now is explain via an example how we do that conversion. This is called dotted decimal notation. There are some slides later on that explain it, but let's just use the example. Dotted decimal notation. What we do is when we have a 32-bit binary value, we break it into 4 parts of 8 bits each. 8 bits, 8 bits, 8 bits, 8 bits. Then we convert those 8-bit values into decimal numbers. With an 8-bit value, the decimal number will be between 0 and maximum value. With 8 bits, 255. With 8 bits, if we can convert to decimal, you've got between 0 and 255. Okay, there's 256 values. So with our 32-bit address, we break it into 4 parts of 8 bits each, and those 8-bit values are converted to a decimal number, and then we separate them, or we join them by dots. So we get 4 decimal numbers separated by dots, and we get what's called the dotted decimal notation. So now, let's convert this dotted decimal notation IP address back to its 32-bit value, the binary value. What do? Use your calculator. Okay. 10's easy though. What's 10 in binary? In binary. Binary addresses. Now we're dealing with a 32-bit address. 8-bit binary, remember? Our IP address is 32 bits. Each of these decimal numbers must map to an 8-bit value. 0, okay, that's an 8-bit value of 10, decimal 10. 2 plus 8 is 10. So the first decimal number 10 can be written as this 8 bits. And then we do that for the remaining decimal numbers. I'll draw the dot here just to separate them. All right, we have another 10. It's going to be the same. $99. What's that? You can check with your calculator. It's just a conversion from 99 in decimal into an 8-bit binary value. And 251? Correct? 251. And remove the dots. We now have our 32-bit real IP address. That is the IP address which is included in, well, that's the value included in the source or destination address of our header. So our computers use binary values, but us humans cannot remember them very easily or cannot write them down very easily, so we convert into some convenient value or convenient form, this dotted decimal form. And the way we convert, if we go backwards, take 32 bits, separate into 4 chunks of 8 bits each, convert each 8-bit binary number into a decimal number, and separate by dots. Okay? So you can go either way. Given the dotted decimal notation, find the binary. Given the binary, find the dotted decimal notation. all IP addresses that we consider in this course, the same applies. Everything that we see, we can convert from one way to the other. Any questions on that conversion? This is just how to convert from binary into dotted decimal notation. You need to be experts on that. You can do it in your head in a minute or two. So you at least understand the steps. Of course, you can use your calculator for the conversion if you want to. You shouldn't need it in most cases. There's other IP addresses in this output. We don't know what they mean yet, but let's see. There's this other one, 10.10.103.255, 255.255.248.0. So there are 3 there. We don't know what they mean, but let's do another conversion. The last one. 255.248.0. Quickly, what's the value in binary? What's next? .255 is all ones, an 8-bit number, 255, so if we put a dot in, is 8 ones. 255.255, 248, is that right? So 255 minus 7, so minus 1, 2, 4, 7 here. So 5 ones, 3 zeros, and 0 of course is just 8 zeros. So we have our 32-bit binary address here. This is a special type of address, not the conversion, it's just a normal IP address, but it's used in my computer for a special purpose. We see the first one was the internet address, which is my computer's IP address. The one we just wrote down is called the mask. And we'll see it described in the slides as a subnet mask. My IP address has 2 parts. One part of my IP address identifies the network, the subnet that I'm on, and another part identifies my computer inside that subnet. So currently my laptop is on one of the SIT subnets inside the internet, and it's one of many computers on that subnet. So in fact, our IP addresses have 2 parts. One that identifies the subnet, and another part that identifies the computer in that subnet. So part of this identifies my wireless LAN subnet, and the rest identifies my computer in this subnet. In your laptop, if you're on the same subnet, you'll have the same part identifying the subnet, but a different part identifying your computer. We'll see some more examples of that later. The mask tells us which bits in the IP address identify the subnet and which bits identify the computer on that subnet. And it's quite simple. Whenever there's a bit 1 in the mask, then the corresponding bit in the IP address identifies the subnet, and the remaining bits identify the computer, which is, how many ones do we have? 8 plus 8 plus 5. We have 21 ones here, and then 11 zeros. That tells us that the first 21 bits in my computer IP address identify the subnet. And if you count the first 21 bits, what do we go to? These bits. The remaining 11 bits identify my computer, or specifically my host. What that means is that inside one subnet, all computers, referred to as hosts, all computers will have the same subnet portion of the address. They'll all have this same sequence as mine, if they're on the same subnet as my laptop. But they'll have a unique host portion. So if there was another computer on the same subnet as my laptop, it must start with this 21 bits, the IP address. And the last 11 bits must be different from mine. Because when we give addresses to devices, they need to be unique. You cannot have the same address. So every subnet in the internet, in theory, has a separate subnet address. Every host or computer inside one subnet has a unique host or computer address. And the 32-bit IP address is the combination of the two of them, the subnet address and the host address. And the way that we tell which bits identify the subnet and which identify the host is from this other address, the mask. Where the mask says if there's a bit 1, the corresponding bit here identifies the subnet. If it's a bit 0, the corresponding bit, so I haven't aligned it very well, but the corresponding bit here identifies the host. So these are the host bits. So in fact, an IP address has two parts. One that identifies the subnet and another one that identifies the computer inside that subnet. And to finish, for example, here's one subnet. If my computer's in this subnet, it's got some address for the subnet. Here we call it LAN 4, but really it is this sequence of bits, this sequence of 21 bits. Every computer inside LAN 4 should have the same sequence for the subnet bits. And they should have a unique sequence for the host bits. Here's another subnet, LAN 1. In our internet, that should have a different sequence for the subnet bits, different from this one. So the first part in this case identifies which subnet we're in the internet. The second part, the host part, identifies the host inside that subnet. And that will be important in how we do routing and how we scale the internet protocol to a global network. But we'll come back to that concept. For now, you should know how to convert the IP address in dotted decimal notation into binary, and the other way as well. And also know at least a subnet mask, this special address, it's still an IP address, tells us where do we split our IP address into subnet portion and host portion. Simply when there's a 1 here, this identifies the subnet. When it's a 0, identifies the host. Any questions on that quick introduction to IP addresses? Yep. Okay, the question is, does the subnet always use the 21 bits as we have in this example? No. It may be different. In this case, it's 21 bits. In another example or another case, it may be 18 bits. So the length here, in our example, is 21. In other case, it doesn't have to be 21. It can be different. It's specified by this other address called the mask. My computer may have this mask. In another network, you may have a different mask, giving us a different length subnet address. Yeah, and that adds some complexity in things. Any other questions? The conversion part's easy. You should be able to, if I give you a quiz in the lecture tomorrow, convert between dotted decimal and binary notation. Then how we use them, for example, splitting into subnet and host portion, becomes more interesting. and harder. If there are no more questions, then yes, there are. So in your, for example, on your iPad, you can see the address of your Wi-Fi address, which is a hardware address. Yeah, an IEEE hardware address with those hexadecimal values, where the first 6 digits are from the manufacturer and the last 6 for your computer specifically. You cannot see your IP address there. Maybe somewhere else you would see your IP address. That shows you the hardware address. You've got one for Bluetooth, one for Wi-Fi. Check on your phone, your tablet, your laptop, find your hardware address and find your IP address. You'll only have an IP address if you're connected to some network. That is, you have internet access. You don't always have an IP address. Tomorrow we'll go back and describe how IP works and then give some more examples of how the subnet addresses and host addresses work. Let's continue that tomorrow.